So thanks so much for coming today. Today I'm going to be talking about using math to design nuclear fusion reactors. So what do I mean by that? Nuclear fusion is a big deal. It's one of these new sort of science fiction sources of energy that we want to try to use to harness the power of the sun to try and produce clean energy for the world. And it turns out that a lot of really interesting math goes into that. So during this talk, I'll tell you about the main candidates for doing nuclear fusion, tokamaks and accelerators. We'll talk about some of the really interesting math that comes up, especially through the topic of hidden symmetries. And in the third part of the talk, I'm going to switch gears from talking about general ideas in physics, with lots of pretty pictures, over to talking about more mathematical concepts, mathematical proofs. So parts 1 and 2 of the talk should be accessible to general audiences. If you're here because you heard about this from somewhere and you don't have that much math background, that's okay. Stick around for parts 1 and part 2, and we'll go through it. There will be some heavy-duty science going on, but it won't be stuff where you'll need to understand all the mathematical details. In part 3 of the talk, I'm expecting people to have a background in multivariable calculus and a little bit of differential equations. In terms of questions during the talk, I am currently planning on just keeping questions for the end, just because there's a lot of material to get through, and there's a lot of people here today. So we're going to keep questions for the end. I'll also have a weekly problem thread if you're receiving pings for that. For the whole week, we'll be discussing all the ideas behind the mathematics of nuclear fusion. Other than that, let's get started. So our goal is nuclear fusion, which is when you take lots of little atoms and you smash them together really fast to get bigger ones. Now, we're familiar with one kind of nuclear energy, nuclear fission. That's when you take big atoms and you break them apart. Fission is kind of dangerous because big atoms are radioactive, like uranium and plutonium. And so they leave behind radioactive waste. So fission is a good candidate for energy, and it's one that we are using right now in the big nuclear reactors that you're used to, but it's not perfect. Fusion, on the other hand, is a lot better. It's much cleaner, it produces a lot more energy, but it's also much, much harder to do. Fusion is solar power. It's the kind of power that the sun is producing. What the sun does is it combines little atoms together through all the high pressure and high energy to make bigger ones, and these reactions produce tons of extra energy. So in order to do fusion here on Earth, we need a super hot, super fast, and very well-controlled reaction. That's not easy to do. The typical fusion reaction that we try to do is combining hydrogen to get helium. In particular, we combine an isotope of hydrogen called deuterium with 1 extra neutron with an isotope called tritium with 2 extra neutrons. When they combine, if you smash them together fast enough, you'll get a helium, and you also get a neutron that flies off. That neutron carries with it a ton of extra energy. We want to capture that energy, feed it back in to continue the fusion reaction, and draw some off to power our world. How are we going to do something like this? I mentioned that our reaction needs to be really hot but really well controlled. It turns out the right tool to use is a plasma. I'm going to tell you what a plasma is in just a moment. And how do we contain a plasma? Well, we use a big magnetic reactor device. There are 2 kinds. The axisymmetric ones. These symmetrical ones on the left are called tokamaks. And on the right, we have the asymmetrical ones. These guys are called stellarators. There are other kinds of devices, like magnetic hammers, magnetic mirrors, other things like that. And they're also interesting, but they're less well used. My research is all about stellarators, but during this talk, we'll also talk a little bit about tokamaks. So what actually is a plasma? Well, you might have heard of plasma as the 4th state of matter. How does that make sense? So we know the main 3 states of matter, solid, liquid, and gas. When you have a solid, the atoms are all arranged in a nice grid. Then as you add energy, the atoms start to float past each other, and they make a liquid. With more energy, they start to be able to bounce around in the vacuum, and that gives us a gas. And add even more energy and make it higher temperature, and now the electrons start to separate from the nuclei. And so you get a big cloud of electrons and ions all flowing against each other. This is called a plasma. So a plasma is really an electromagnetic gas. Plasmas have a couple different properties. One of the properties is this property called quasi-neutrality. Because we have all these electrons and ions flying around, you might expect that if you're standing in a plasma, you feel a lot of electric fields everywhere. But actually, you really barely feel any at all. This is because of electric field shielding. When you're standing in some spot and you look at some ion, you might expect it to impart an electric force on you. But really, there are a lot of electrons swarming around it. And there are just enough electrons swarming around that ion due to its attraction to cancel out all the forces you feel from far away. This is called Debye shielding. So plasmas are mostly neutral. You don't really feel electric fields in them. So then how are they electromagnetic? Well, it turns out that there are other ways to generate magnetic and electric fields, from Maxwell's laws of induction. So what are the laws on the bottom right here? The top two laws are laws about producing electric fields from charges. And these guys we don't see because of quasi-neutrality. But on the bottom, we see that we can produce electric and magnetic fields. E is for electric field and B is for magnetic field, if we have moving charges. So for example, J here, which is the current, says that if we have charges moving around, which we do in a plasma because we have a gas of electrons and ions, then that produces a magnetic field. And on the other hand, when we have a changing magnetic field, that produces an electric field. So we get induced magnetic and electric fields in a plasma. And these guys are going to affect the motion of the particles. So now the particles get affected by the magnetic and electric fields, and the magnetic and electric fields get affected by the particles. And so there's a chain reaction of self-organizing behavior in a plasma, which makes them pretty complicated to study. There are two kinds of ways that people study plasmas. There's the physics way and the math way. On the physics side, we arrange plasmas into a couple different areas. The main three are astrophysical plasmas, which are like the interior of the sun, Earth's core made of molten magma, the solar wind, the stuff that makes up galaxies' arms. Astrophysical plasmas can either be really hot or really cool, but they're always really big. On the other hand, we can study fusion plasmas, which are still really hot, but they're much smaller. They're small enough to fit in our reactors down here on Earth. And for fusion plasmas, we care a lot more about stability and trying to get energy out of them. That's what I study. Finally, we have low temperature plasmas. These are plasmas that are used in industry, for example, for producing semiconductors. There are more plasmas out there. People who study lasers often deal with plasma. But these are the main three that you'll see if you ever end up going to study plasmas yourself. But that's just on the physics side. On the math side, we don't care about whether you're studying an astrophysical plasma, a fusion plasma, or a low temperature plasma. Instead, we care about what kind of mathematical equation you're using to understand the plasma. At the top here, we have the most detailed and the most difficult to solve equation, the Vlasov equation. The Vlasov equation treats your plasma as if it's a bunch of gas particles that are just bouncing off of one another through their electric forces. It's really, really hard to study. We're going to see it on the next slide. Then we can get simpler to gyrokinetics, even simpler to two fluids, and then the simplest possible model for studying a plasma is magnetohydrodynamics. Okay, that's a big fancy word, but the idea is that we're coupling magnetism with hydrodynamics, which is the flow of fluid. And what I study is even simpler than that, MHD equilibrium. This is what we care about seeing inside of a reactor. A nice stable plasma that isn't moving too much and is able to produce energy. So here are these crazy equations. On the left, we have the Vlasov equation, and you can see that there are so many equations. There are derivatives involved, there are integrals involved. We call this an integro-differential equation. And whether you want to study the Vlasov equation mathematically or simulate it on a computer, it's going to take a ton of work to do. In the middle, we have the MHD equations. Okay, this is still pretty scary, but at least the integrals are gone. So this is just a differential equation at this point. What do the MHD equations actually do? The top three equations here are the Navier-Stokes equations. They tell you how a fluid flows. The bottom 4 equations here are Maxwell's equations. They tell you how the electric and magnetic fields change. And so we couple them together to get one big set of equations. Finally, we have the equilibrium equations. This is what happens when you take MHD and you simplify it as much as possible. Now, there's only 3 equations. We only see B, the magnetic field, and J, the current. And so we've simplified things a lot. But these equations are actually still really, really hard to solve. They're so hard that in the kinds of reactors that we design, we don't even know that they always have a solution to begin with. We don't have an existence theorem for these equations. But what's good about them is that we can study them pretty easily using simulations on a computer. And that's going to make all of what we talk about for the rest of the talk possible. We'll also talk about some of the theory of these equations. For example, let's try to understand how a plasma actually moves. Okay, the first thing that we can say about a plasma is that the magnetic field lines determine everything. If you have the magnetic field traveling in one direction, then the particles are going to follow it. But they don't follow it exactly. Instead, they spiral around it in these gyro orbits. So the ions spiral one way, and the electrons spiral the opposite way. As the particles move, they gyre around in these really, really tight curls and follow the magnetic field lines one way or the other. Okay, but that's just the first order behavior. As they spin, depending on the magnetic field, they can experience some drifts off of their magnetic field line and onto another. There are 3 kinds of drifts that occur in a plasma. There's the curvature drift, the grad B drift, and the E cross B drift. Okay, it's going to be important for us to see what each of these is, so let's talk about it. They're a little bit weird. They don't do what you expect. Let's start with the curvature drift. If your magnetic field is bending, then the particles are going to drift one way or another. But instead of drifting in the direction of the magnetic field, which is the direction they try to travel mostly, or in the direction of the curvature, instead they drift perpendicular to both. So whatever the direction of the magnetic field is and the direction of the curvature, we pick a direction that's perpendicular to both of those. The ions are going to go one way, and the electrons are going to go the other way. The direction depends on the charge. Another drift is the grad B drift. This is when your magnetic field is increasing in strength as you go from left to right. Then, if the magnetic field is increasing in strength in one direction and it's pointing in another, the drift is going to be perpendicular to both of those directions once again. The ions are going to drift one way, and the electrons will drift the other way. And finally, we have the E cross B drift. This one's a little simpler. If you have an electric field and a magnetic field, then particles are going to drift perpendicular to both. And this time, ions and electrons drift the same way. Figuring out each of these drifts by going through the equations is pretty difficult. But once you know them, you can study these equations pretty effectively, just thinking about the dynamics of particles. Okay, so let's get from talking about MHD to trying to actually contain a plasma in a chamber. This is the study of plasma confinement. Okay, so on the left here we have a magnetic field line, and it's just going straight in one direction. It's not going to do a very good job at confining a plasma. Particles will spin around it in one direction, but they're going to continue along it forever and ever, and they're never going to stay in one sort of container. So to fix this problem, let's take this magnetic field line and let's bend it into a circle. This is better because now if you have a particle and it's spinning around, it's gyro orbiting around this magnetic field line, it'll just go around and around forever. Okay, well, this would be good except for one problem, the drifts that we just talked about. But before I show you what happens with the drifts, let me tell you how you would actually do this. How do we produce a magnetic field that looks like this straight line or this circle? We use Maxwell's laws. So you might have played with an electromagnet when you were a kid, which is where you take a wire and you coil it around, say, a screw, and then you put power into it, and it makes it magnetized. So what we do is very, very similar, but at a much larger scale. We take big coils of electric wire, spin them around in circles, and then power them up all at once. And it leads us to get a magnetic field that shoots through them. Okay, in order to do this in a circle, you just arrange your big magnetic coils, or your big electric coils, in a circle. So this is why all these shapes that you see for tokamaks or stellarators are going to have these big coils in big circles around them. Now let's talk about the problem with drifts. So say you have a magnetic field line that's curving around in a circle inside of your donut reactor. First things first, particles are going to experience a curvature drift. The curvature is pointing inwards, and so because the magnetic field is going through the donut, ions are going to drift upwards and electrons will drift downwards. Okay, so we'll accumulate some positive charge at the top of the reactor and some negative charge at the bottom. And this is okay because as the positive charges accumulate at the top and the negative charges accumulate at the bottom, they're going to attract each other. And so eventually this will balance out and they'll stop shifting away. But once you have this charge asymmetry, our quasi-neutrality from before is ruined. And we get an electric field pointing from the plus charges down to the minus charges. Uh-oh, now we have a second drift, the E cross B drift. With B going into the donut and E going downwards, both the ions and electrons are going to feel a force pushing them straight out of the reactor towards the walls. They'll get slammed into the walls of the reactor where, well, they're really, really hot. If we're trying to do fusion, they're just going to melt the walls of the reactor. So this is really, really bad. So we need to make sure that we avoid this problem of drifts. It seems like all hope is lost for toroidal confinement. But it turns out things are okay as long as we take an idea from the gyro motion of the particles around B. Let's make the magnetic field move in a helix itself. Okay, so now the magnetic field line is moving in a big helix. But remember, also the particles are moving in tiny little curls around the magnetic field line. So there's a lot of helixing going on. Now the curvature drift just points towards the middle of the donut, the axis of the device. And so particles are going to drift forward or backwards along the donut, which isn't bad at all. That's totally fine. So in this sort of setting, we've alleviated the problem of the drifts. But there's still going to be a little bit of drifting out and in, and so we do need to make sure that over many turns around the device, your particles' drifts cancel out, so they stay nicely in the device. Okay, that's going to be a problem for us to solve later, but for now, let's see what the two big ideas that come out of this idea of wrapping our field lines into circles are. One of the types of devices that we have is the tokamak. The tokamak does exactly what we just said. It's a symmetrical donut where we take a magnetic field line that's going around in a circle and we have to wrap it up into a helix. In order to do that, you use a transformer in the middle. You might have heard of transformers. They're those things that sometimes explode during crazy storms. These guys change voltages between one wire and another. And for a stellarator, they allow us to drive this helical motion in the magnetic field. This is great because it's not so hard to define, but on the other hand, it makes life a little bit more complicated because we're pumping a lot of energy into the plasma, which tends to destabilize it. So we want to be careful of doing that. On the other hand, we have stellarators. Stellarators are much, much harder to design. They're asymmetrical. But they naturally bend the magnetic field lines due to their asymmetry. So you can see that the magnetic field lines here are kind of bending around, curving along the stellarator. And this bending happens because the magnetic field is designed to be asymmetrical from the start. So we can naturally induce helical motion without having to drive any extra energy. So stellarators are a lot more stable. But it's much, much harder to design these so that all those drifts that we talked about evenly cancel out at the end. Okay, I included one picture here of how that tokamak transformer works. I'm going to say it quickly, but if you're curious about this after the talk, feel free to ask questions about how a tokamak works. We have our transformer in the middle. It's a bunch of coils that are stacked together. You power them up and you increase the voltage and the current through these coils as you're operating the tokamak. That produces by induction a magnetic field that's increasing, which produces by induction a current around the torus that's increasing. Actually, that current's just constant, it's not increasing. But that constant current is enough to produce the helical motion of field lines. Okay, this is a pretty complicated design, and you can see why it might destabilize the plasma to have all these extra magnetic and electric fields going on in the background. Now let's see what's going on inside of a tokamak, or a stellarator. Now that we have one, we've contained our plasma, what's actually happening to those magnetic field lines as they travel around the helix? We can use something called a Poincaré plot to study this. To do this, we just take a cross-section of our stellarator, or our tokamak, and we look at every time that a magnetic field line hits it. Every time that it hits it as it goes around, we mark that point a specific color. Each magnetic field line is going to get its own color. This is called a first return map. Okay, so what are the dynamics inside of a stellarator? Here's a cross-section of one of these asymmetrical stellarators, and inside we see three kinds of things happen. For the most part, the magnetic field lines sort of go around in a circle. These are called flux surfaces. And if they're nicely nested from the axis at the center of the device all the way to the wall, then we say that our stellarator has nested flux surfaces. This is great because it means that our particles in the middle that are staying on the magnetic field lines will be contained inside of the plasma. Okay, so what you can imagine here is that you have a magnetic field line that's hitting here, it goes around the circle, maybe it hits at a different point, and then a different point, and so on and so forth, but as it goes around many times, it fills in one of these circles densely. We can have other kinds of behavior, though. For example, we can have these magnetic islands. Magnetic islands happen when your magnetic field line is going around in a nice rational number. And so it can split off into sort of a polygon shape like this. In this case, we have 5 islands in this island chain. Magnetic islands are actually a bit of a problem, and we're going to see why on the next slide. But the worst problem of all is when we lose the structure totally, and we end up with chaos. Sometimes the magnetic field lines just go all over the place, and they're totally unstructured. We really want to avoid this. It tends to happen near the walls of the reactor, so we want to reduce that region of chaos as much as possible. Why is it important to try to reduce islands of chaos? Because the whole point of using a plasma for doing fusion is that we can get a really nice temperature gradient. With the magnetism, we can levitate the plasma in the air using our big coils as it moves around the device. And so we can get the really, really hot part of the plasma, which is just as hot as the sun, to stay in the center of the device. As you move from the center all the way out to the edges, things get a lot cooler. They'd better because magnets only operate well when the temperature isn't too hot. And in fact, some of the magnets that we use, which are superconducting magnets, need to be at some of the coldest temperatures on Earth. So you need the hottest temperatures on Earth right next to the coldest ones. How are we going to achieve this? Well, we need to keep a really good temperature gradient. The temperature needs to be super hot in the center and fall off quickly as you go to the edges. Which means that hot particles near the center had better not leave where they are. Okay, but if we have islands, we run into problems. Because a particle that's somewhere in the near the axis part of the island, near the middle of the reactor, is going to get carried by its magnetic field line to sometimes be on the outside of the island. And so the temperature will equilibrate, it'll be just as hot on the inside of the island as it is on the outside of the island. We really want to avoid this as much as possible. It's losing space that we have to keep our temperature gradient nice and hot. Here's one of those flux surfaces extended out from its cross-section around the device. You can see that it's allowed to change shape as it goes around. As long as we take one cross-section and understand what's going on there, we can understand what's going on in other parts of the device as well. And here on the right is a picture of a real plasma experiment. This is going on in Wendelstein 7X, which is one of the big stellarators that exists in Germany. I'll show you a picture of the outside of it later. But for now, what you can see is that inside the plasma that's flowing around the device does actually form one of these flux surfaces. So this mathematical formalism is really a good way to understand what's going on. Okay, we're going to start heading from part 1 of the talk to part 2. I've talked about how the magnetic field lines can move around in nice flux surfaces, but we know that the particles are drifting. We know that these islands occur, leading to weird magnetic topology. And we also took a lot of approximations to get from the Vlasov equation, which was very descriptive, to the magnetohydrodynamic equilibrium. How do we guarantee that our particles are actually contained within the plasma? This is where a really special tool comes in, called Noether's theorem. Noether's theorem says that every symmetry in a physical system is going to lead you to gain a conserved quantity for the physical system. Usually we don't think of symmetries and conserved quantities as being related, but Noether's theorem says that they're actually in one-to-one correspondence. So, for example, when we have an axisymmetric nuclear reactor, it leads the particles to conserve their flux surface. The particle will actually stay on its flux surface while the reactor runs. We're going to go through a proof of this fact in the second half of the talk, where you'll get to see in practice how Noether's theorem works. What this means is that symmetrical devices like tokamaks are perfect. They keep the particles contained. And so if you can deal with this problem of the plasma being destabilized by all the extra energy you're pumping in, then you know that your plasma is going to be contained. You'll get it to be able to be really hot and still be able to do fusion, which is great. When you lose axis symmetry, you lose all guarantees of containment. There's no guarantee that the drifts are going to cancel out and that your particles are going to stay on their flux surfaces. But it turns out that we can go back to Noether's theorem and we can study what's the minimum amount of symmetry that we need in order to get particles to conserve their flux surface. We call this amount of symmetry quasi-symmetry. It's this hidden symmetry in the device. This device at the bottom here doesn't look very symmetrical, but there's a series of steps that we can go through to figure out whether or not particles will actually be contained by Noether's theorem. In a quasi-symmetric stellarator, all the drifts are going to cancel as we go around and around the device. Let's talk about what quasi-symmetry actually is. Okay, this slide I'm just putting in here for fun. If you're curious about this, I can include a reference to see how you actually do this. But this is how we go from our Lagrangian for the system. We apply a symmetry, and it leads us to a conservation law. At the bottom here, we have the formula for quasi-symmetry, which is really complicated. This is what Noether's theorem is helping us to do. But let's talk about something a little bit more down to earth, a little bit more of a geometric understanding of what quasi-symmetry actually is. Okay, I'm going to read to you the definition. It's going to have a lot of buzzwords in it, but then we're going to unpack it and understand exactly what's going on. So, a stellarator is quasi-symmetric if, in Boozer coordinates, the contour curves of the magnetic field strength all form straight lines. Okay, that's a lot of words. Let's go through each. First of all, what are Boozer coordinates? So if you've taken multivariable calculus, you might remember the difference between rectangular coordinates, cylindrical coordinates, and spherical coordinates. Boozer coordinates are another option. You get them once you have a magnetic field. What are our three coordinates? Our first coordinate here is called psi. It's this blue coordinate here. And psi tells you which of the flux surfaces you're on. So as you increase psi, you move from the middle flux surface, the magnetic axis, all the way out to the wall of your reactor. Your choice of psi tells you which flux surface you're sitting on. The second coordinate is phi, the green coordinate here. Phi tells you how far you are along a magnetic field line. Remember that the magnetic field lines are pointing around the device in the toroidal direction. They're going in helices, and as you increase phi, you move further and further along a given magnetic field line. And our final coordinate is theta. Theta tells you which magnetic field line to pick along a given flux surface. As you increase theta, you move around one of the flux surfaces. Okay, so these are Boozer coordinates, and it turns out that if you graph certain quantities in Boozer coordinates, we can find out a lot about the plasma. For example, let's graph the magnetic field strength. The magnetic field is a vector field. It's just a bunch of vectors. Let's graph the length of each vector. For bigger lengths, we'll color it red. For shorter lengths, we'll color it blue. We'll end up seeing that there are lines, contour lines between colors. Each line in this plot, each curve, is a curve that represents the magnetic field having the same strength everywhere on that curve. Okay, so a stellarator is quasi-symmetric if when you plot its magnetic field strength in Boozer coordinates, the contours form straight lines. So this guy is not very quasi-symmetric because the contours are curvy, but this guy was really, really quasi-symmetric because in its Boozer plot, in the coordinates in the Boozer plot, the magnetic field strength is really, really nice and straight. Okay, so this is what quasi-symmetry means. We end up having three different flavors of quasi-symmetry. The first one is quasi-axis symmetry. This is when your lines in your Boozer plot just go from left to right. So remember that one of our coordinates is just the distance along the magnetic field line. As you go from left to right, you're increasing phi, which is just how far you are along the magnetic field line. So left to right is the direction that particles move, or right to left. So in this case, the particles are sitting on vectors that always have the same length. The magnetic field strength never increases or decreases. This is important because of what the energy of a particle is in a plasma. A plasma particle has two different sources of energy. One is kinetic energy, that's its mass times v squared over 2. The other is the magnetic energy. That's the strength of the magnetic field at that point squared divided by 2 times the magnetic constant. So the more strong the magnetic field you're in, if you're conserving energy, the less speed you can have. But in this case, particles keep the same speed as they go from left to right, because the strength of the magnetic field doesn't change. Next, let's talk about quasi-poloidal symmetry. This is when your magnetic field contours are going from bottom to top. Now, as particles travel from left to right along the magnetic field lines, they have to go up and down these big hills and valleys. When it's at its strongest, the magnetic field energy is going to contain most of the energy of the particle, and so it'll have less speed. When it's in one of the wells, then the particles can speed up really fast. You even have some particles that don't have enough energy to get over the hills, and they bounce back and forth. These guys are called trapped particles. Okay, little side plot, which we won't talk too much about here at all. Usually, instead of quasi-poloidal symmetry, we care about something called quasi-isodynamic stellarators, or omnigenous stellarators. These guys still have the contour lines that go from bottom to top, but they're allowed to bend, as long as they all bend together in unison. It turns out that that's not so bad. Now, this is kind of an interesting side topic, but try saying quasi-isodynamicity 5 times fast, and you'll see why I decided not to talk too much about this during this talk. Okay, finally we have quasi-helical symmetry. This is when, in the Boozer plot, the magnetic field contours are not going left to right or up and down, they're going diagonally. Still, when a particle travels from left to right, it has to go up and down these humps. But quasi-helical stellarators are much more common because there are so many different options for how to build them. So quasi-axis symmetric, as we saw at the start, and quasi-helical stellarators are the most common ones. Now, it's not easy to find a quasi-symmetric stellarator. Because the definition is so opaque, it's very difficult to design one by hand. For example, look at this kind of Mobius strip-looking stellarator on the left. On the right, we can see that its Boozer plot doesn't have totally straight lines. Well, it looks like maybe it's getting there. Some of them are kind of straight, and we've got these humps in the middle that aren't quite straight. How could we nudge the stellarator to try to make it more quasi-symmetric? Okay, so we have our geometric definition of quasi-symmetry, but we need something that we can compute and plug into a computer to understand better what's going on. This formula down here is a big nasty formula, but it's not hard for a computer to actually calculate. So FQS here, if your stellarator is perfectly quasi-symmetric, this guy will be 0. All of these variables are just variables about the plasma. B is our magnetic field, psi is our flux coordinate in Boozer coordinates, m and n are the slope of quasi-symmetry. Okay, so one of them is the horizontal, and one is the vertical. So I guess it's n over m is the slope. Iota, g, and I are also related to the plasma. We don't need to worry so much about the formula, but what we do want to do is use this formula to actually use computational optimization to design our quasi-symmetric stellarators. So how do we do optimization of a stellarator, starting from nothing? First, we're going to parameterize our plasma shape. To do this, we usually use a Fourier series. Then, we're going to pick some objectives that we want to achieve. For example, maybe we want our stellarator to be quasi-symmetric, we want the helical field lines to bend a certain amount, that's called rotational transform. Maybe we want it to have a certain volume, so that we can do enough fusion. Then we optimize. We start with some random plasma boundary, we solve the MHD equilibrium equation inside, numerically. There are a lot of different ways we can do this. There are codes like VMAC, SPEC, or DESC. Now that we have the solution, we know what B is, and so we can compute things like how quasi-symmetric is our stellarator, what's its rotational transform, and so on. And we can take those answers that we get and use them to nudge our stellarator, perturb it to get a new boundary for the plasma. We can choose the direction to perturb it using an algorithm like gradient descent, which you might know from things like machine learning. And then we repeat over and over until our stellarator is honed to be as quasi-symmetric as we can get it. So, for example, in this picture here, you can see that we have a stellarator that just looks symmetrical. It's just a nice tokamak donut. But maybe we want an asymmetrical device instead. Let's see if we can perturb it to something else, ruin the quasi-symmetry, but then get the quasi-symmetry back. We nudge it again, and again, and again, and again, and as we nudge it, that Boozer plot is going back to being very nice and straight. So you can see that this guy looks a lot like this guy. They're both this kind of Mobius strip shape. But we've managed to get almost perfect quasi-symmetry in our final result, using a computational optimization algorithm. In the last maybe 8 years, we've been able to get really, really far just by doing computational stellarator optimization. Our old Boozer plots didn't look that good at all, but now we're achieving stellarators that are almost perfectly quasi-symmetric, and might just be able to do fusion when you build them. Okay, but just because you have a shape for your plasma doesn't mean you can actually produce it. How do we find magnetic coils that shape the plasma just right? We need to do optimization again. This is stage 2. We parameterize our magnetic coils, also using a Fourier series. We pick some constraints like the length of the coils, how far apart we want them to be, and how curved they are. And then we optimize. Start with some set of coils, solve for the magnetic field that they produce. This is using the Biot-Savart law on the bottom here. And then we ask, how good is the set of coils that we produced at producing the plasma boundary that we want? Then we perturb the coils, and we do this over and over again until we get a good set of magnetic coils. Okay, here we see 2 examples of magnetic coils. On the left, we have a sort of lumpy plasma. Maybe this isn't so quasi-symmetric. But the coils that they've produced that fit this plasma are really, really simple. They're just circles, there's only 6 of them, and as long as you position them in the right places, you get this plasma. On the other hand, we could try to produce a really quasi-symmetric stellarator, but then the coils are going to be really, really complicated. So we need to achieve a balance between coil simplicity and how good your stellarator actually is. This matters a lot. Okay? So as a theoretician, I don't like to think about this stuff, but what happened at Princeton was they tried to build this stellarator called NCSX. It had 18 very complicated coils that needed to be super precise. They only had a 1.5 millimeter tolerance. They used tons of fancy instruments to try to build this device. They had an $100 million budget. Eventually, they were up to an estimate of $170 million, and their project got canceled before they could even finish it. So it really, really matters to not only design your device so that mathematically it works really well, but also so that the engineers and physicists and experimentalists that are trying to build it and do experiments with it can actually build it in the first place. So this is something that, I've had to get used to, going from working on pure math to working on something that affects the world. But in the end, there are a lot of really good stellarators out there. So let me talk to you about a few of them before we move to the heavier math part of the talk. In the top left, we have Wendelstein 7X. I showed you a picture of the inside of this before. It's 5-fold symmetric. It's really big. It's located in Greifswald, Germany, which is in the north. And Wendelstein 7X is kind of the flagship stellarator around the world. It's really good for doing lots of experiments. It's not good enough to do nuclear fusion, but it's great for understanding better how plasmas work when we try to contain them. On the right, we have the Columbia Non-Neutral Torus, CNT. This guy's a lot of fun because as a student at NYU, I get to take the train up to Columbia and meet the people who work on this. Monthly, we have meetings with them to talk about our findings and what we're working on day to day. It's also kind of cute because its coils are linked. In the bottom left, we have Muse over at Princeton. So sure, one of Princeton's stellarators got canceled, but they've built another one, and this one's a lot simpler. The coils for the stellarator are actually totally symmetrical. The reason it's asymmetrical is because they speckled the surface with all of these magnets. These are permanent magnets, just like the ones that we would play with when we were kids. So they've speckled the surface with a grid of these in just the right way to nudge the plasma so that as it goes around the device, it bends into a stellarator. I was lucky enough to do some research on Muse over the last year. It's really cool. And then on the bottom right, there's another stellarator that's important to me. This is HSX, which is at the University of Wisconsin. HSX is 4-fold symmetric, and it's special to me because when I went to University of Wisconsin last summer, I got to slap its coils, stick my head through the middle, and just enjoy learning about it from the people who work on it every day. There are other stellarators around the world, and there are other ones being built right now. For example, there are startups that are working on building stellarators that they claim will be able to do nuclear fusion. It's a good way to maybe get lots of investment money, and maybe they'll make some great advances that'll help us as a community to further understand how to contain a plasma and get nuclear fusion to work.